Hey everyone, welcome back. Today we're going to go a little bit more in depth into a topic that I touched on just briefly in a previous video, which is bank switching on the ZX Spectrum Next. And it's actually a topic I've been kind of trying to avoid because it's kind of a complex topic that's a bit involved. But I guess we have to get through it at some point, and I've got my new Sinclair shirt on, so I should have motivation to go through it now at any time. So let's get started with it, and we'll make our way through it because it is an important topic, and it's one that is actually very useful, particularly if you're going to be making larger programs. Now, as you probably know, the ZX Spectrum Next computer comes with either 1 megabyte or 2 megabytes of RAM already installed. However, the ZX Spectrum Next also contains a microprocessor, which is an 8-bit microprocessor, the Z80, which has an 8-bit data bus, but a 16-bit address bus. And that means the address bus is only able to access 64 kilobytes of memory at a time. So there needs to be some sort of process or functionality in place that allows the computer to access all that extra memory, up to 1 megabyte or 2 megabytes of memory. And the way that it does it is by using this function called bank switching. So as I mentioned, this can be quite a complicated topic and confusing topic to wrap your mind around. So before we get started, I just want to go over some terms that I'll be using in today's video to help clarify things for us. And the terms are right here on my screen, which are slot, bank, and page. Now, the term that we use to describe this function of swapping memory in and out of the computer's addressable space is called bank switching, and there are different terms for it that you might hear. You might hear bank swapping or paging, and there are different terms that are used to describe the same purpose, the same functionality. So I want to just define how I'm going to be describing the terms in this video for today. And the first term we're going to look at is the term slot. So since the Z80 microprocessor is only able to access or address up to 64 kilobytes of memory at a time, it gets divided up into different sections, which are called slots. And those slots are areas that we can swap physical memory in and out of. So let's go on to our next term here, which is bank. So the bank switching capability, the whole purpose of it, as you may know, is to swap sections of physical memory inside the computer in and out of these addressable slots. So these physical memory sections are called banks. But now you see I have another term here called page. So what is a page? Well, we don't actually really technically need the term page, but it can help to clarify in some situations for the following reason. There are actually two methods that the ZX Spectrum Next computer uses to perform this memory swapping function, and the main difference between these two methods is the way that it divides up the memory, and in particular the size of the different slots of the memory and the different banks of memory. So these different sections of memory can be divided up into either 16 kilobyte slots or 8 kilobyte slots, or 16 kilobyte banks and 8 kilobyte banks. So I'm just going to use this term page here just to refer to the method that uses the 8 kilobyte memory section sizes. And this is also known as the MMU, or Memory Management Unit method. And we're going to be discussing all of these things again shortly, but I just wanted to give you a brief introduction to the different terms that I'll be using. So just to go over it quickly once again, when we talk about the term slot, that refers to a portion of the addressable memory that the Z80 microprocessor can access. And that's a slot that we will be swapping memory in and out of. And the term bank refers to a section of the physical memory, either the 1 megabyte or 2 megabyte memory that physically comes installed in the ZX Spectrum Next. So it gets divided up into 16 kilobyte banks. And if we're using this other method of dividing up the memory into 8 kilobyte sections, which are otherwise known as MMU, or Memory Management Units, then I'm going to use the term page to refer to these 8 kilobyte memory management unit physical sections of memory. Now, before we go any further, why don't we take a look at the manual that comes with the ZX Spectrum Next, and I'll just bring it over here. So here we're looking at chapter 24 of the manual, which is titled the memory. And I'm just going to go down to a few sections that are describing this memory swapping technique we're going to be discussing today. And let's start right here with this section labeled the memory map. And let's take a look at these highlighted sentences. And the first one here says, the ZX Spectrum Next has a 16-bit address bus, and this fact means the computer can see 65,536 bytes, or 64 kilobytes, of memory. So this refers to the addressable memory that the Z80 CPU can actually see at any one time. It's only able to access or address up to 64 kilobytes of memory, and that's what this sentence is saying. So let's go down now and take a look at the next section that says, the computer uses a memory access technique known as bank switching. In this technique, there's a distinction between the maximum addressable memory, the amount of memory that the CPU can see, i.e. 64K in our case. So that's what we just described, that the Z80 processor can only see a maximum of 64 kilobytes of memory at any one time. And then it goes on to say, and the amount of physical memory in the system is the other type of memory that we are concerned with. In the ZX Spectrum Next's case, the physical memory is divided into equally sized portions called banks. Or in this video, I'm also going to be using the term pages, as I just mentioned, for the 8 kilobyte sections of memory. But it says in this paragraph that the memory is divided into equally sized portions called banks. And the 64K of memory that the computer can see is also divided into the same sized portions called slots, which we discussed. And then finally it says, a virtual map of sorts is constructed that tells the hardware what physical memory bank appears in each of the 64K's slots. So what this means is we're not obviously actually physically swapping memory in and out of these slots, and we're not moving physical memory from the physical memory chips into physical memory addressable slots, but rather we're just setting up some pointers by using a program to tell the computer which slot of addressable memory points to which bank of physical memory. So let's read on now and see what else we can learn about this memory banking or memory switching or memory paging functionality. So down here on the next page, titled Memory Management, it says, there are two banking schemes employed in the ZX Spectrum Next, standard and MMU based banking. So these two different schemes, which are used to swap physical memory in and out of memory slots, they use different sizes of memory banks. And you can see in this diagram here, I'll just zoom in a bit. So the standard way of doing this memory swapping technique or this bank switching technique is to divide the memory up into 16 kilobyte areas, which is shown in this diagram here. So here there are 4 different sections of 16 kilobyte slots. So the addressable space in this case is split up into 16 kilobyte sections. And that is the standard method of bank switching. But there's also another method of bank switching, which is known as MMU bank switching, right here, MMU scheme. And we'll go down and take a look at that scheme now, which is described at the bottom of the page here, where it says the MMU or Memory Management Unit scheme is diagrammed below. It is much more flexible in that it can map any 8 kilobyte bank of physical RAM, which is the memory obviously, into any 8 kilobyte slot of the CPU's addressable memory. And here's a diagram here that shows these different MMU slots. It says right here, MMU based memory map. And this shows that the addressable memory space that the Z80 processor can see here is divided up into 8 equal sections, which are 8 kilobytes each, and they are labeled or numbered from MMU 0 to MMU 7. And here these numbers here show the different memory addresses where are the boundaries of those different sections. So now let's go back to my notes here and we'll take a look at that in a bit more detail. So here let's first take a look at a chart that I made that shows the different sections of the memory and the way it's divided up. And first let's take a look at this leftmost column right here, which is labeled addressable memory, which we know is 64 kilobytes in size because that's how much memory the Z80 microprocessor can see at any one time. And this 64 kilobytes of memory is divided up into these different sections here, which I'll go over in just a moment. But for now, let's just take a note that these addressable memory slots range from address 0000 hexadecimal to FFFF hexadecimal, which in decimal would be 0 to 65535. And let's take a look how they're divided up. So as we just mentioned, we need to divide up the addressable memory space into slots that we can swap memory banks in and out of. So here is how the addressable space is divided up. So you can see over here, it's divided up into 8 sections. For example, this top section goes from address 0 to 1 FFF. Then the next section goes from 2000 to 3 FFF and so forth. But also there's colors here, pink, yellow, green, and blue, which highlight 2 slots as the same color. And the reason we have 2 slots highlighted here together is when we're referring to the 16 kilobyte method of doing this bank switching technique. Now, in today's video, I'm actually going to be focusing on the MMU method of swapping memory in and out of these slots, which I'm also going to refer to as pages. If you look right here, I refer to 8 kilobyte pages. So as we just took a look at, there are 2 different methods the Spectrum Next uses for doing this memory swapping technique. And the standard method uses 16 kilobytes slots and banks. And the MMU method, or memory management unit method, uses 8 kilobyte slots and banks, or pages. So let's just quickly take a look at the numbers in this chart so we'll be familiar with both of these methods, just in case we want to use either one. And so here, let's take a look at the next column here, which is labeled 16K slots. So if we wanted to use the standard method of memory swapping or bank switching, we would have the memory divided up into 16 kilobyte slots, and they are numbered. They're numbered from 1 to 4. So there's 4 16 kilobyte slots in the standard method. They are slot number 1, slot number 2, slot number 3, and slot number 4. And these numbers show you where these slots start and stop in the addressable memory space. So for example, slot number 1 here, you can see goes from address 0 to address 3 FFF. Slot 2 goes from address 4000 to address 7 FFF. And slot 3 goes from address 8000 to address B FFF. And finally, slot 4 goes from address C000 to FFFF. So that's the 16 kilobyte method of doing this memory swapping. Now let's take a look at the MMU method of doing memory swapping, which uses 8 kilobyte slots, which is right here, 8 kilobyte slots, MMU. And these 8 kilobyte slots are numbered from 0 to 7. So that might be confusing because the 16 kilobyte slots start at number 1, and the 8 kilobyte MMU slots start at number 0. And they are numbered, like I said, from 0 to 7. So these ones have their own addressing ranges as well. So here slot number 0, for example, ranges from address 0 to address 1 FFF. And then slot number 1 ranges from address 2000 to address 3 FFF, and so on. So this is how the addressable memory is divided up into either 16 kilobyte slots or 8 kilobyte slots. And these are the slots of memory that we're going to be swapping physical memory in and out of. Well, actually, we're not physically swapping memory in and out of them. Actually, when we create our programs, it's just going to set up a pointer that tells the computer which section of memory to use when it's using any particular slot. So the computer will know when it's addressing any particular slot that that particular slot is mapped to a particular bank of memory in the physical memory space. So let's just take a look at the rest of our chart here, and we'll look at how that physical memory space is divided up. So for now, let's just skip over this center column here that's labeled MMU register. We're going to be taking a look at that a bit later when we go through our programming examples. But let's take a look at this column here, which is labeled default 16 kilobyte bank. As I mentioned, these memory slots are mapped to particular physical memory banks in the computer. So the slots each have a bank associated with them, and when you first turn on the computer, there are default banks or default pages associated with each of these physical slots or addressable slots. And one other thing we should keep in mind is that these slots and banks get automatically updated depending on which method we use. So let's say we decide to use the MMU method of updating these slots to point at a particular bank in memory, then the 16 kilobyte addressing method will automatically get updated. So we don't need to worry about the 16 kilobyte method being out of sync with the 8 kilobyte method, because they both get updated at the same time, regardless of which method we choose to actually use. Let's take a look at how the physical memory inside the computer is split up into banks or pages. And I have a chart down here that shows that right here. And you can see here that this column on the left is labeled 16K bank, and the next one is called 8K bank. So these are the two different methods that we can use to do this memory swapping technique. We can either split up the memory into 16 kilobyte banks or 8 kilobyte banks. And what this is showing is the way the banks are numbered. So for example, let's take a look at this 16 kilobyte bank column, and just ignore these top rows here for now that have no numbers in them. But if you look down here, we see that the first bank is numbered 0 right here. And then depending which computer you own, which version of the ZX Spectrum Next you own, whether it has 1 megabyte of memory installed or 2 megabytes installed, that will determine how many physical memory banks are in the computer. So for example, if you have an unexpanded 1 megabyte ZX Spectrum Next, it will have 16 kilobyte banks that are numbered from 0 to 47, which means it will have a total of 48 16 kilobyte banks. And if you have a 2 megabyte ZX Spectrum Next, then you will have 16 kilobyte banks that are numbered from 0 to 111. So in that case, you will have a total of 112 different 16 kilobyte memory banks. And the reason that it's not exactly double the amount, you might think, well, 2 megabytes is double 1 megabyte, so why don't I have 47 multiplied by 2 as my total when I'm expanding my memory with double the amount of memory? It doesn't work that way, because part of the initial memory that's installed, that initial 1 megabyte of memory, gets used up for other things. So we don't actually double the amount of banks when we add that second megabyte of memory, but we actually get to utilize that entire extra 1 megabyte of memory, which is why we get to add more banks than just an extra 48 banks. So although we might expect that doubling the amount of physical memory would increase our number of banks from 48 up to 96, it actually increases it up to 112. So it numbers from 0 to 111. Now let's take a look at the MMU version of this method, which uses 8 kilobyte banks right here in column number 2, which I'm also calling pages, just to help differentiate them from the 16 kilobyte method. So the MMU method, I'm going to be using the term pages, as I mentioned. And of course, if we're using 8 kilobyte slots and 8 kilobyte pages or banks, then we should have twice as many of them, because they are half the size of the 16 kilobyte slots and banks, right? And that's exactly how it works. So you can see here, if we're using the 8 kilobyte bank method or the MMU method, then we will have banks in our physical memory numbered from 0 to 95 in the 1 megabyte ZX Spectrum Next, or 0 to 223 in a 2 megabyte ZX Spectrum Next, which would give us a total of 96 8 kilobyte banks or pages, or 224 8 kilobyte banks or pages numbered from 0 to 223. Now we don't really need to concern ourselves with the rest of this table. One thing that is somewhat interesting is this next column here labeled true addresses. So these are the actual physical addresses of the memory inside the computer that is associated with these different banks. And you can see that these numbers are quite high. They're way higher than obviously a Z80 microprocessor can address. So that's why we have to use this bank switching technique, because these numbers are so high. But we don't actually need to concern ourselves with the actual true physical addresses that are associated with these banks and pages, because we're going to be using this bank swapping technique, and we're going to kind of get around having to use these actual physical true memory addresses. Now there's one more chart I want to show you, which is this one here, and this one identifies the purpose or the default use for some of those different banks that we just took a look at. So let's take a look at, first of all, the 16 kilobyte banks. So we know that the physical memory inside the ZX Spectrum Next is divided up into either 16 kilobyte banks or 8 kilobyte banks or pages. There are certain banks in the physical memory that are pre-allocated to serve a particular purpose. And this is how they are numbered. So if you take a look here, 16 kilobyte banks 0 through 13 have these uses or kind of purposes assigned to them by default, which corresponds to 8 kilobyte MMU pages numbered from 0 to 27. So although I think it is possible to play around with these pages and banks and kind of change the way that they're used, we have so many pages and banks to work with. I think when I'm creating my programs, I'm just going to not fool around with these ones, and I'm going to do my paging or my banking using pages and banks that start with numbers that are higher than these maximum numbers. So for example, you can see here the 16 kilobyte banks range up to bank number 13, and the 8 kilobyte banks or pages go up to bank number 27. So for example, in today's video, we're going to be looking at the MMU bank swapping technique or page swapping technique. And I'm going to be swapping in pages that are higher than number 27 because I don't want to mess around with these different banks that have some default purposes already assigned to them. So hopefully that's all clear. Remember, we have the addressable space that's divided up into slots, and we have the physical memory that's divided up into banks or pages, and we're going to be swapping the physical memory banks or pages into the addressable memory slots. So let's take a look at some programming examples now and see exactly how that works. All right, now before we take a look at some programming examples, let's go back to my description here where I describe the different memory areas and how they're split up. And there's one more thing we should take a look at, which is, although we just took a look at how the physical memory is divided up into different banks, and some of those banks have default purposes assigned to them. For example, in the MMU paging technique, we can see that 8 kilobyte pages numbered from 0 to 27 have some default purposes assigned to them. Well, this is the physical memory banks that we're talking about, but what about the addressable memory slots? They also have some default purposes assigned to them as well. So if we take a look at those, which is right here, let's concentrate on just the 8 kilobyte slots, which is used in the MMU bank switching method, and they are listed right here from slot number 0 to slot number 7. And let's take a look at how they are used by default when the computer is first turned on. So first let's take a look at here slots number 0 and 1. If we take a look over here on the right side under the description column, it says that slot 0, for example, is normally ROM. So ROM, as I'm sure you know, is the section of memory where the computer keeps all of its instructions and operating code that it needs to start up and perform certain important functions. So we don't want to mess with the ROM normally. So for example, I wouldn't want to experiment by swapping banks of memory into slot number 0 because I don't want to mess up the ROM. And similarly with slot number 1, that is also used for ROM, so I'm not going to be swapping any memory banks into slot number 1 today. And let's take a look at slot number 2, for example. It says normally used for normal/shadow ULA screen or tile map, and then slot number 3 also has a function timex ULA, extended attribute graphics area, and tile map, and so forth. So I'm not going to mess with slots number 0 through 3. So they have default purposes that seem to be somewhat important. I'm not going to mess with those. It may be possible to swap memory in and out of those slots if you know what you're doing, but just to be safe, I'm going to avoid those for today. And I'm going to focus on the upper 4 slots, which are slots numbered 4 to 7. And these encompass the address ranges from 8000 hexadecimal to FFFF. So here we have 4 slots we can work with, and that's going to allow us to swap memory banks into these 4 different slots, and we can play around with it and see how that works. Although there are a couple of notes here that we might want to take a look at that refer to a couple of these different slots, particularly slot number 4, which is at address 8000, and slot number 7, which begins at address E000. So let's see what notes I've written here. So for slot number 4, it says note, VS Code or Visual Studio Code. And when I say Visual Studio Code, this really just refers to whatever editor you happen to be using. I happen to be using Visual Studio Code, but it says VS Code start address is at the start label by default, and I'll show you that in a moment. In the VS Code template, so if the org statement puts start at 8000, then the program will be overwritten if you swap a bank into this slot. So this is something we're going to have to take note of, and in case this is confusing to you, I'm just going to rephrase it for you because we haven't actually taken a look at the program yet, so don't worry if this doesn't make sense to you yet. But essentially what this means is when we create our Z80 assembly language program, or when I create my Z80 assembly language program today, I have to tell the computer where in memory that code is going to get assembled to once it gets converted into machine code. It needs to get converted into machine code and stored beginning at a particular memory address. So for example, if I tell the computer to store my code at an address which is in slot number 4 in this address range of 8000 hex to 9FFF hexadecimal, then obviously if I swap a piece of memory or a memory bank into this slot, that's going to overwrite my program. So that's one thing we need to be aware of, and I'll show you that specifically when we take a look at the program, but I just want to give you a bit of a heads up now. And then other note I want to take a look at is this one here, which refers to slot number 7, and it says note SP or stack pointer. And if you're not familiar with the stack already, then this might be confusing to you, and you might want to go back and watch the video that I made describing the stack and how it works and the stack pointer. But just as a quick summary, the stack is a special area of memory allocated for storing particular data that the computer uses, or we can also use that particular area for our programming as well. But for example, when the computer calls the subroutine, it needs to know where to continue execution of the program after it returns back from a subroutine. And the way it does that is by pushing or storing a value onto the stack. To put it another way, it stores a value into the memory location that is allocated as the stack. So to put it simply, the stack is a location in memory that we want to be careful with and make sure we don't mess with it. So we don't want to overwrite the stack because that will probably crash our program. And my note here says SP stack pointer is set to FF40 by default in Visual Studio Code template or whatever editor you're using. So it will be overwritten if you swap a bank into this slot. So just as I mentioned a moment ago, if I were to tell the program to save my code beginning at address 8000, then if I were to swap a bank of memory into this slot, that would overwrite my code, which I don't want. And similarly, I have to be careful with slot number 7, because by default, the stack pointer is set to point to an address that lives in slot number 7. So if I again were to swap a bank of memory over this code in slot number 7, that will erase the data that's in the stack and my program will probably crash. So I just want to give you a bit of a heads up about these two slots that we need to be careful with, and I'm going to describe this again in detail when we take a look at it specifically in our programming examples. All right, time to get into some fun stuff, and we're going to actually do some coding here, and it's going to be fun coding because again we're dealing with colors, and everyone loves dealing with colors, and particularly changing the border color, which is always fun. So there is actually a very important concept that I'm going to explain to you, which I recently learned, which had me confused for a long time because I'm not really familiar with it, but I'm going to share with you what I've learned about it. And of course, I'm not an expert in memory bank swapping, and there's lots of aspects to it that are new to me still, but I've learned enough of it that I can actually use it, which is fantastic. And I'm going to share what I've learned with you. And if you want to learn more about it, then of course you can just read the manual in the sections that I was just looking at. But I want to share with you a concept that is important and potentially confusing, which is the concept of swapping memory banks into physical addressable memory slots. Now, it might not be confusing to you to understand that we have physical memory and addressable memory slots, and we're going to be swapping physical memory banks into addressable memory slots. That part is not so confusing. But what I found confusing is that there are actually two methods we can use to do this. And the reason that this was confusing for me was because I always just assumed that they were interchangeable and I could choose whichever method I want, but actually they're not interchangeable, and there's a very important difference between the two. And the main difference between them, and of course I'm going to show you exactly how they work in a moment, but just to let you know what the difference is between these two different techniques, is that one technique occurs as the program is running, which is called during runtime, and the other technique occurs during assembly, so when the program is being assembled. So you're probably already familiar with Z80 programming enough to know that there are certain tasks or instructions which are known as assembler directives, which take place or get executed as the program is being assembled. However, once the program is completed and assembled, then once it gets executed, those assembler directives have already been completed, so those don't run during runtime. And that's the difference between these two different memory switching techniques. One occurs during runtime while the program is executing, and the other occurs during assembly when the program is being assembled. And they both actually have some very important uses. So let's take a look at both of those techniques in this one program I've created, and I'm going to go through it step by step for you, and you should be able to understand everything in this program now based on the tutorials that I've made up until this point. Well, they're not actually supposed to be tutorials, they're just supposed to be me documenting my journey, but if you can use them as tutorials, that's great. We can all learn together. So let's take a look at this program, and this program that I'm showing you now is of course the template, or based on the template that I used when I was setting up my development environment to begin with. And if you haven't watched my video on that, you can go ahead and take a look at that if you want. But this is the default template program that I'm using to create my Z80 assembly language programs for the ZX Spectrum Next, because as you should know, the development environment that I've set up automatically or semi-automatically executes these programs and runs them in the CSpect emulator, which of course emulates the ZX Spectrum Next. So let's go ahead and take a look at this program now, and we'll see how we can experiment with some memory bank swapping techniques. So first of all, I want to introduce you to the top part of my program here, just so we're not missing anything and nothing is confusing to you. This is part of the template, and here where it says device ZX Spectrum Next, that sets up this assembler to know that my program is designed to be used in a format compatible with the ZX Spectrum Next computer. So I keep that in all of my programs. And then this next line here, cspect map project.map, that creates a file called project.map when this program gets assembled. And the purpose of this map file, as I found out, is to allow labels to be displayed in the CSpect debugger. And if that doesn't mean anything to you, then don't worry about it. We're not going to be covering that in today's video, but I leave that line in my template as well. Now this next section of code that I have here, which I've put a comment called memory page loading executed during assembly. So what that means is this section of code right here is going to take place during the assembly portion of the program, when the program gets assembled. So these lines of code are not going to get executed during runtime when the program gets executed through the CSpect emulator. These are all going to get executed as the program is being assembled. And this is really useful, and I'll tell you why. Because what we're doing here, before I get into the code itself, is what we're doing here is we're going to be swapping memory banks, physical memory banks, into addressable memory slots like we discussed, and then we're going to load up that memory slot with some data, actually just one piece of data, and then we're going to swap a different bank into that same slot, and we're going to load a different piece of data into that bank, and then we're going to just repeat the process. And what we're trying to do here is we want to swap different banks into the same slot and then inject piece of data into that bank. So that what we're doing here is preloading essentially some memory banks with data. And this is very useful so that when we assemble this program and it creates a .nex file for us, that .nex file will automatically contain all of the data that we've preloaded into these memory banks. And the way that that happens is if we look down at the bottom of the program template here at these Save Next options, this option down here right at the bottom that says Save Next Auto, that is the option that is going to, well, there's a note right here that says what it does. It says generate the NEX file automatically based on what pages you use. So this Save Next Auto option is going to tell the assembler to save all the data that we've preloaded into memory banks when it creates this .nex file, which is great. That means we don't have to load up data into the memory banks during runtime as the program is executing. Now, just before we leave this section here where we're talking about the Save Next options, and if you're not familiar with Save Next options, then you may want to go back and watch the video that I made on setting up this development environment, where it refers you to a website where you can research what these Save Next options are. And I'll put the link in the video description below. These are options that refer to this SjASMPlus assembler that we're using. So it tells the assembler certain things, that it sets it up in certain ways. And I just want to take a look at a couple of these other options before we leave this section. In particular, I want to take a look at this option here, which is the top line here where I have a line that reads Save Next open project.next. And here's a note here that says what this line actually does. It says this sets the name of the project, the start address, and the initial stack pointer. So these are very important things to be aware of. Obviously, the name of the project is important. Ours is going to be called project.nex, and we're saving our assembly language program with the name project.asm. And once it assembles, it's going to be creating a file called project.nex that we can run in our emulator. And then the next thing it says that it indicates is the start address. So you can see here, there's a word start. So what this start word here means, it's actually indicating a label, which is telling the assembler where we want our program to begin executing when it runs through the CSpect emulator. And this start word here is referring to a label which is right here. Here's a label here called start. And so when our program gets converted into a .nex file or gets assembled into a .nex file, once it runs through the CSpect emulator, it's going to start running at this part of our program, which is indicated by this word start or this label start, because that is what we have printed right here, start. And you could change this if you want to have your program start execution at a different point if you want. For example, if I were to change this word start to sub2, which is a subroutine in my program, then when my program gets executed, it will begin running at this point in my program, which is indicated by this label called sub2, for example. But I want my program to start at the start, so I'm going to leave this start word here because it's going to start running at this label position here called start. And finally, let's take a look at this last option, which has a value of hexadecimal FF40, and it says this is the initial stack pointer. So as I kind of gave you a heads up a moment ago where we discussed how the stack is an important part of the memory in the computer and it needs to be preserved, otherwise it could corrupt the program and it could crash. This value tells the computer where to put the stack, and this is the value that it's going to put into the stack pointer register. And in this case, you can see it has a value of FF40, and you can of course change this value to whatever you want, but let's just take a look at this default value of FF40, for example, and try and figure out which memory slot is this value located in. So I'm going to go back to my notes here, and we're looking for the address FF40, and it should be right down here, somewhere in this range, in slot number 7, which ranges from address E000 to FFFF. So obviously address FF40, which is this address right here, is going to be located somewhere in slot 7. And why is that important to us? Well, that's important to me because that tells me I shouldn't try to swap any memory banks into slot number 7. So I'm not going to do that. So if I go back to my notes here again, we want to find a slot that we can play with safely, which means we can swap banks of code into safely without overwriting anything important. So if we go back to my template here, let's take a look at where my program is actually being saved in memory. And as I just discussed, it's being indicated by this start label, which is right here. Here's the start label here. And the start label is immediately following this org instruction, or this org directive, which says org hexadecimal 8000. So that means any code that follows this org statement is going to get saved at address beginning at 8000 hexadecimal. So that means in this case, when I assemble this program, the machine code version of this program is going to be stored at beginning at address 8000 hexadecimal. So what slot is 8000 hexadecimal in? Let's take a look at my notes again. And 8000 hexadecimal is right here in MMU slot number 4. So that means I don't want to try swapping any memory banks into slot number 4. So slot number 4, I need to leave alone. Slot number 7, I need to leave alone. So that leaves me with 2 slots I can play with, slot 5 and slot 6. And remember, we're talking about MMU 8 kilobyte slots. So let's go back to my program here. And now that we know that we have slots number 5 and 6 available for us to play with, let's see how we can actually swap some memory banks. So first, let's take a look at the top section here, which are assembler directives. So the first instruction we can use to swap banks in and out of slots is this MMU instruction right here. And the way it works is just like this. For example, this instruction says MMU 6, 50. And what that's going to do, if we take a look at the note here, it says swap 8 kilobyte page 50 into MMU slot 6. Very simple, very easy to use instruction. It's very self-explanatory really once you know how it works. It's going to take physical memory bank or page number 50, and I use the term page because that helps me, as I mentioned, clarify that I'm using the MMU bank swapping method. So in this case, I'm telling the computer to swap bank number 50 or page number 50 into MMU slot number 6. And this is going to happen during assembly. And then what's going to happen next? Well, the next instruction here I have is an org instruction. So why do I want an org instruction? Well, in this case, I want to save a byte of data into that memory bank that I've just swapped into slot number 6. And specifically, I want to save a byte of data into the first address of slot number 6. So what is the first address of slot number 6? Well, we can easily figure that out by looking at my notes again at slot number 6, which is right here. So slot number 6 has an address range from C000 to DFFF. So obviously the first address is address C000. And that is why in my program I'm using an org instruction or an org directive followed by the address C000, which represents the first memory slot or the first memory address in slot number 6. So address C00 is always the first address in memory slot number 6, no matter which bank we swap into it, because remember, this is addressable space we're talking about. Slots refer to addressable space, so those addresses never change. So in this case, what I'm doing is indicating a particular memory address, which is C000, which is the first address in slot number 6. And then what do I want to do? Well, here I have a define byte instruction. And as we know, a define byte instruction simply stores a byte of data into memory. And in this case, since it's following an org instruction, and the org instruction indicates a memory location C000, it's going to save a byte of memory into location C000. And what byte of data is it going to save? Well, it says right here, underline BLK, which is a label. And so, of course, I've assigned a value to my labels, which I do right here. I just used some EQU instructions, which we took a look at in previous videos. And so here I'm just assigning numerical values to these labels representing the different colors. So for example, underline BLK right here contains a value of 0, which represents the color black. So what's going to happen up here is, if we go through this just one last time to make it clear, The first line here, MMU 6,50, is going to swap memory bank number 50, or memory page number 50, which is 8 kilobytes in size. It's going to put that into memory slot number 6. And then after it does that, it's going to store a byte of data, in this case a value representing the color black, and that value is the number 0, and it's going to store that in address C000, which is the first byte in slot number 6. Okay, so let's take a look at our next section of code here, which says MMU 6,51. So very similar to our first part of the code, this one is going to swap bank or page number 51 into slot number 6. So now we're changing the physical memory bank that we just swapped in. We just swapped in bank number 50 into slot number 6. Now we're going to swap in bank number 51 into slot number 6. And again, we're going to have an ORG instruction indicating address C000 to point to the first memory address in slot number 6. And here I'm defining another byte of data, but this one has a value representing the color blue, which is a number 1. And then if we go on down, so on and so forth, we just keep incrementing the bank number from 50 to 51 to 52, 53, 54, 55, 56, and 57. And we keep swapping these banks one by one into memory slot number 6. Why? Because I want to end up by having 1 byte of data stored in each of these memory banks, these physical memory banks, and that byte of data is going to represent a color, which I'm going to use to change the border color later on in the program. So all of these instructions here get executed during assembly time before the program even runs. It's going to occur while the program is being assembled. So here, as I mentioned before, we're preloading some data into some memory banks. And now let's take a look at this part of the code, which assigns values to labels. So here I'm assigning the values of hexadecimal 50 through 57 to these labels here called MMU slot 0 reg, which stands for a register, which I'll get into in a moment, through this label here called MMU slot 7 reg. So here I'm just assigning some numeric values to these labels called MMU slot something reg. And then if we look down here at the next part, I'm doing the same thing, but this time I'm assigning values to these labels that are called MMU slot whatever add, which stands for address. And if you take a look right here, you'll see a value that we should recognize now, which is C000. We now know that C000 is the first address in memory slot number 6, and that's why it's being assigned to this label called MMU slot 6 add or address. So we know that the MMU slot 6 address equals C000. So this just lets me use this label MMU slot 6 address instead of C000. And then finally at the bottom here, I've got my color numbers assigned to colored labels as we just took a look at. All right, so now we should understand that when the program is being assembled, it's going to automatically load memory banks or memory pages into slot number 6, and it's going to load a color value into the first address of that slot or that bank, and then it's going to swap in different memory pages into slot number 6, ranging from bank or page number 50 to bank or page number 57. So that's what happens when the program is being assembled. Now let's see what happens when the program actually executes. So we'll go down here to the main part of my program, and you can see here is our org statement, which says org 8000. So our machine code version of this program is going to be stored at address 8000. And the org statement actually doesn't specifically mean store the program at address 8000. It means store whatever code comes after this org statement at this address that's indicated. So you can have more than one org statement in a program, as we do here. We have an org statement here, which is indicating where the start of our actual executable code is going to be saved. And we have org statements up here in our MMU instruction code sections, which store bytes of data into memory banks that we've swapped into memory slots. So let's see what our main section of code here is going to do. So now remember, we have our color bytes of data already preloaded into certain memory pages when this program even starts execution. And let's see what we're going to do with the data that's been preloaded into those memory pages. So here we have a modular program, as you know. So the first section of this program, identified by this start label, it does only two things. It calls two subroutines. Here it's calling a subroutine called sub1, and then here it calls a subroutine called sub2. And it says right here what these subroutines do. It swaps in an 8K page, and then it sets the border color. So what this program is going to do when it executes is it's going to swap in those pages that we preloaded with those color bytes into slot number 6, but this time it's going to do it during runtime, and then we're going to extract those bytes of data and use those values to change the border color. So let's see how we do that. It's pretty simple, but it involves using another instruction that we haven't taken a look at yet, which is the runtime version of this memory swapping technique, which is right here, next reg. So next reg is an instruction that is used for many purposes, and we're going to be using it for a particular purpose, which is to do this memory swapping technique. So next reg executes during runtime, as opposed to MMU, which executes during assembly time. So that's an important point to remember. Now let's take a look at how we're going to do this. So the first thing we're going to do is call subroutine number 1, called sub1 right here. And the first instruction is this next reg instruction. And the way this one works is exactly the same as our MMU instruction. Remember, with our MMU instruction, we indicated a slot number and then a memory page number or bank number that we want to swap into that slot. It's the same thing when we use the next reg instruction, except in this case, instead of using a slot number, we need to use a register number. So if we take a look up here where I've defined some values, we can see that these numbers here, 50 hexadecimal through 57 hexadecimal, these are the register numbers that we're going to need to use in order to do this memory swapping using the next reg command. And I've assigned these numbers to these labels called MMU slot whatever reg. So for example, value 50 is assigned to MMU slot 0 reg, value 51 is assigned to MMU slot 1 reg, but in this program we're only going to be swapping memory banks or memory pages into slot number 6. So I really only need to worry about this label here, which is MMU slot 6 reg, which is the register that allows me to swap a bank into slot number 6, and that register number is hexadecimal 56. So let's go back to my program here, and you can see that is the label that I'm using, MMU slot 6 reg. So how this instruction works is it swaps a particular bank or page of memory into a slot, and remember these are 8 kilobyte pages, and so in this case I've indicated number 50, which is bank number 50. Now don't get confused by the fact that this 50 number here is also the same number as the register number. So don't get confused between the number of the bank that we're swapping in and the register that we need to put in this instruction. So in this case I'm using MMU slot 6 reg, which has a value of 56 hexadecimal. So if I wanted to, I don't of course need to use a label. I could replace this MMU slot reg label with a hexadecimal value, which would be 56. So if I wanted to, I could just replace this with $56, just like that. So I don't need to use a label there, but I just do that to make it easier for myself. But this is how you would do it without using a label. You just put next reg and then the register number, which is 56, which represents slot number 6, and then the bank number or page number, which in this case is page number 50. And then I have my return instruction, which returns back up to my main program loop up here. So now this first section of code, or this first subroutine, has swapped page number 50 into slot number 6. And then what do? Well, we're calling another subroutine here, sub2, which is right here, sub2, and it says it sets the border color. So let's see how we're going to set the border color now that we've swapped page number 50 into slot number 6. Well, here we're going to assign a value to the HL register pair. And this is MMU slot 6 add label, which if we look up here, is right here, MMU slot 6 add, which equals C000, which we know very well by now is the first address of slot number 6. So I'm assigning that address to the HL register pair. And now what I'm doing in the next line here is I'm extracting the byte that we stored into that first address and I'm putting it into the A register. And why am I doing that? Because I'm going to use that A register in the next line to change the border color using this out FE instruction. And that's exactly what that does. And you can check my notes here just to make it all clear for you. It says right here in my first line, set HL to first address in MMU slot. And this is actually MMU slot 6. So I could just put 6 here because this program only uses slot number 6 because we determined that's one of the safe slots for me to use. And then the next line here says get color byte. So then we want to extract the value of the color from the first address in that slot. And then we want to set the border color using this out FE instruction. And then this JR, which is relative jump or jump relative $, will jump to the same instruction location. So this jump relative instruction just jumps to the same program counter location over and over again. So it continuously re-executes this jump relative instruction. And so it effectively pauses the program forever, just re-executing this jump relative instruction continuously, indefinitely. So now let's try and figure out what we would expect to happen when we run this program the way it is. Well, let's go through it and take a look. So our first part of the program is going to call subroutine 1. And what happens in subroutine 1? We execute a next reg instruction, which is going to swap in a memory bank into a memory slot. And in this case, it's going to swap in memory bank or memory page number 50 into slot number 6, which is represented by this register number 56. So the next reg instruction, as I mentioned, performs other functions besides just memory swapping. But since I'm using register number 56, that tells this next reg instruction that I want to do some bank swapping. And then I have to tell it which bank I want to swap in. And here I tell it I want to swap in bank number 50. And it already knows which slot I want to put that bank into because I've given it register number 56, which represents slot number 6. So hopefully that's all clear now. So this first line here will swap memory bank number 50 into slot number 6. And then it returns and it calls sub2, which is going to load the HL register pair with the first address of that slot number 6. Then it's going to extract the value that's been stored in that address, put it into the A register, and then use that value to change the border color. So in this case, what value would we expect to see? Well, bank number 50 or page number 50 has been preloaded with a value, right? So which value has been preloaded into that page? Let's take a look back up here at our assembler directive section. And right here, we swapped in page number 50 into slot number 6 and then loaded C000 with the color of black, or the value that represents the color black, which is value 0. So when we run this program now, I would expect the border to change to black. So let's go ahead and run it and see if that's true. So I'm just going to run it by executing a batch file called make.bat. And again, I explained how to do this in my previous video where I explained how to set up this development environment. And so let's go ahead and run this program now. And there we have our CSpect emulator indicating a border which is black. So let's escape from this now and go back to our program. And now, so we've just confirmed that slot number 6, which has been loaded with bank number 50, actually does contain the value that represents the color black. So this preloading step that I did of preloading the colors into these banks seemed to have worked. But let's confirm that by loading in a different bank. So let's see which bank or page do we want to load in. So let's say we want to change the border to cyan. And where do we do that? Which memory bank would we need to swap in to slot number 6 in order to get a cyan color? Well, right here you can see that the cyan byte or the cyan value has been loaded into this memory bank here, 55, or preloaded into bank 55, because remember that happened during assembly. It doesn't happen during runtime, but now we're going to extract that value during runtime. So let me go down now and change our bank number or page number to 55. And I'll do that right here. I'm just going to replace this number 50 with 55. And of course I need to save this program again as project.asm. So I've just saved it. And now if I run it again, I would expect to see a cyan border. So let's give it a try. And luckily it works. And there we go. So that is a hopefully somewhat easy to understand explanation of how the memory bank swapping functionality works. Remember, all we need to do is swap banks from physical memory into addressable memory space. And we just need to keep some considerations in mind in terms of which banks we want to use. There are some banks that have been predetermined to have particular purposes that we might want to avoid using. And similarly, there are some memory slots that have been predetermined to have some purposes. So we may either want to avoid using those slots, or we may want to manipulate our program so that it's safe for us to use those slots. So that's a brief introduction. Well, not that brief, but it's, like I said, it's not an easy to understand topic necessarily, and hopefully I covered it in a way and explained it in a way that is somewhat easy for everyone to understand. But there is a lot of information on it in the manual that comes with the ZX Spectrum Next, and you can download that manual online as well. But I'm focusing here on how we would do these techniques, of course, in assembly language, since the manual tends to focus a lot on basic or next basic in particular. But this is how we can cover this kind of complex and somewhat confusing topic in assembly language. And hopefully that made sense to everyone. And I want to thank you all for watching, and we'll keep moving forward in our game development journey. And I'll see you in the next video. Take care. Actually, there's one more thing I want to show you before we go, which is another program that I created, which automatically cycles these banks in and out of these memory slots and changes the border color automatically based on which bank is loaded into this slot number 6. And just in case you're interested in doing this yourself as a challenge, you might want to give this a try just for practice. But I'll show you the program that I used to accomplish this. And I'll just go through it quickly here without explaining in too much detail. So if we take a look at this program, my start section contains one instruction which calls subroutine number 1, which is right here. And what sub 1 does is it loads HL with a value representing the memory slot number 6 address, which we know is C000, shown right here. And then it loads a value into B, which is value number 7, since I'm going to be using that as a counter, both to count the colors and the page number offsets. So the next line of code here, which loads a value into the A register, it starts off by loading a value of 50, and that 50 represents bank number 50 or page number 50. As you can see up here, we started off with page number 50, and we went from page 50 to page 57, and those banks store 1 byte of data each, and those bytes of data represent the colors ranging from black to white. And so what this program is going to do is automatically load those banks into slot number 6, extract that color byte from the first memory address, which is C000. It's going to change the border color based on that value, and then just keep cycling through all these banks and do it all over again endlessly. So that's what is happening here. First, we load this slot number 6 address, which is C000, into the HL register pair. And then we load a counter, which is 7, into register B. And then I'm loading a value of 50, which represents bank number 50 or page number 50, into register A. And then here I'm adding those two values together. And the reason I'm adding them together is because I'm going to be decrementing B every time as we go through this loop. So I need to reinitialize A with a value of 50, and I just add this offset, which is in the B register, to it, and that determines which bank or page we're dealing with. So these are going to range from page 50 to page 57, but actually in this program we're going to be counting down from page number 57 down to page 50, and we're going to cycle through that over and over again. So in our next line here, we have our next reg instruction, which we just looked at, which actually swaps that bank or page into slot number 6 right here. And we do that using this next reg instruction that we just took a look at. So that's what's happening here. We're swapping a bank, which is 57 in this case when the program starts, into slot number 6. And then in our next line here, we're extracting the color byte from the first address in that bank or slot number 6, putting it into the A register, changing the border color based on that value, And here we have a DJNZ instruction, which is decrement jump not 0, which you probably already know how that works. It decrements the B register, and if it's not 0, it jumps. And here it's going to jump to this label called loop 2 or dot loop 2, which is right here. And this dot loop 2 is what's known as a local label. And if you're not familiar with local labels, you can go back and watch the video I made on that. But what that is going to do is cycle through this section of code, which is going to decrement the bank number and load it into slot number 6. And each bank contains a different color number. And this section of code is going to tell the program to cycle through bank number 57 down to bank number 50, or page 57 down to page 50, and extract the color byte, change the border color, and then just keep doing that over and over again. And that's what this final instruction here, jump relative dot loop 1, does. It tells the computer to start this whole process over again by resetting our loop counter B at 7 up here. And that just keeps happening over and over again. So let's go ahead and run this program and see what happens. There you go, that's kind of cool. So there's a little challenge that you can try for yourself. If you like, you can either copy my program, or you can modify it, or come up with your own program. And you can maybe experiment to see how you can swap banks in and out of memory slots and change the values, both during assembly time using the MMU command and during runtime using the nextreg command, and just play around with it and have fun. And I think it's going to be quite important to understand this concept if we get to the point where we're creating longer programs that require us to use more of the memory space that comes with the ZX Spectrum Next. So again, thanks for watching. Hope you enjoyed the video, and we'll see you next time.